Okay, so with this, we use the concept of the surface energy to understand the grain boundary structure, the angles between them, etc. But then the question is also, what if you have completely clean surface? How will that surface look like? So, for example, if you have silicon material, and if you cleave it in ultra-high vacuum, the question is, what will happen with the surface atoms, right? If you have silicon and you cleave it in air, for example, it will automatically form oxide. But if you do this in ultra-high vacuum, what will happen with the surface atoms? So we mentioned the fact that if you cleave a material, so every time when Professor Ross is here, my computer freezes. So the question is, when you cleave the surface, what happens with the material itself, right? So last time what we learned is that if this is the bulk of the material, there will be bonds that connect the atoms. And again, this is a very simplified case where each atom is surrounded by 4 other atoms, nearest neighbors. So we mentioned if you cleave that surface, there will be dangling bonds at the surface that are formed. And they will contribute to the surface energy of the material itself. And we use this concept to calculate the surface energy by calculating what is the number of the atoms, how many bonds do you break, what is the density of the atoms, etc. But in real situation, what happens with these dangling bonds? Will they just stick out, or what will happen? So this is closely related to a very large subfield of material science and physics that is called surface physics. And it turns out that these dangling bonds will reconstruct. What that means is that these 2 atoms will form, in this particular case, a double bond instead of a single bond. What that means is that these 2 atoms will be bonded more strongly than this atom with this atom here. So again, what is the consequence of this analysis is that their position, or their relative position within the crystal, will be different from their equilibrium position in the crystal. So just to explain what that means, is that, again, if you're looking at the cross-section, so this will be a single bond within the bulk, right? So this is bulk of the material, and this is surface. And if these 2 atoms, instead of forming 1 bond, the dangling bonds from these atoms will connect, so you will have a double bond. So, and again, because the strength of this bond is stronger than the single bond between individual atoms, they will come closer and form this type of architecture. And again, if you look at this material from the top down, so you're looking from the surface itself, you will then see double bonds, and you will see that the atoms have very different configuration than what would be their configuration in the bulk material. So, for example, if you looked at this material from the top down, within the bulk, the atoms would have the cubic symmetry, right? So there would be 4-fold rotational symmetry. In this particular case, this is lost, so you remain with a 2-fold rotational symmetry. What that means is that, again, the symmetry within the bulk is very different from the symmetry of the atom position at the surface itself. And this is called surface reconstruction. So, and for many years, these type of things have been postulated, and people would argue that the properties of the atoms at the surface must be very, very different from the properties of the atoms within the bulk. But relatively recently, what that means is in the 1980s, it has been demonstrated for the first time, it was directly visualized how the surfaces of the materials look like. So this would be one of these images. So this is scanning tunneling microscopy image. Of a silicon 111 surface. And you can see these very beautiful features at the surface. So this is silicon 111, right? If in silicon has a cubic structure, right? It's diamond type of crystal lattice. And you would certainly not expect this type of surface atom positions if you simply follow the symmetry of the underlying bulk crystal. And this is very famous 7x7 surface reconstruction. It simply means that the periodicity on the surface is 7 times periodicity of the underlying crystal. And different types of crystals and different types of materials will have different surface reconstruction. And in order to obtain these beautiful images, you have to cleave silicon in ultra-high vacuum, right? So these types of measurements are done using the scanning tunneling microscopy, which uses a very small tip to measure the current between the tip and the material. And you have to first cleave the material within the vacuum and then transfer everything within the vacuum and measure it on the surface, right? And these types of experiments now can be done routinely, and these types of measurements and images can be obtained relatively straightforward. Again, before 1980s, this was impossible to see. So what that means is that, again, this is yet another example of where the theory and the predictions in material science were somehow more advanced than the techniques that we use. But again, luckily, we can visualize this directly. Okay, so with this, we are finishing the discussion about different types of defects in crystalline materials, right? So we talked about first point defects, and we learned that these are thermodynamically stable defects. What that means that at a finite temperature, there will be a certain number of point defects that are intrinsic and characteristic for that material. Then we talked about dislocations. We learned how they're introduced. So these are one-dimensional dislocations. We mentioned that they determine mechanical properties of the materials. And then we eventually learned about surfaces and other types of defects, surface defects, stacking folds, and we learned about the surface reconstruction.